welcome back. We're in the end of chapter problems here. I did one problem earlier. Let's continue on with it. So in this next problem, it says you have two loudspeakers in a 20 Celsius room. They emit 686 hertz of sound waves along the x-axis. At 20 Celsius, they're telling you that the speed of sound is 343 meters per second. It says if the loudspeakers are in phase, what is the smallest distance between the speakers for which the interference of sound waves is maximum destructive? So it's destructive, in other words. Well, let me get my chalk here. More chalk. So you have so we know the speed of sound. We know the frequency. Let's calculate the wavelength. Just get that out of the way. Out of the way. The wavelength will be the speed divided by the frequency. The speed is 343, and the frequency is 686, and that's nice. This is half of that, so this is 0.5 meters. So 0.5 meters. Now, let's draw a picture here, part A. Here's speaker 1, let's say, and here's speaker 2. And the distance between them, if the position of this one is x1 and the position of this one is x2, then the distance between them is delta x. And we know that delta phi, that controls the constructive or destructive, is given by 2 pi divided by the wavelength times delta x plus delta phi 0. This is the phase between the two speakers. So they say if they are in phase, so for part A, in phase, that means delta phi 0 is 0. Okay. What is the smallest distance between the speakers, that is delta x, for which the interference is destructive? We know that if you want constructive interference, you need this. For constructive, you need m times 2 pi. This thing has to be m times 2 pi. And if it's destructive, this is m plus a half times 2 pi. And this m here is 0, 1, 2, and so on. I mean, obviously, if delta x is 0, if they are at the same spot, they are in phase, that would be constructive. But we want to put them far away enough that it is destructive. And when is it first destructive? Well, that's for the smallest m. So when m is 0, you get 0 plus a half is 1/2 of 2 pi, that's pi. So we want this thing to be equal to pi. So first, the left side will be pi. In here I have 2 pi over lambda times delta x plus 0. Delta phi 0 is equal to 0 because they are in phase. And so the pi goes away. And so delta x will equal to lambda over 2. And that is 0.25 meters. Let me just check. I have it correct? Yeah, that is correct. Let's go to part B. Let's read it. It says, if the speakers are out of phase, what is the smallest distance between the speakers for which the interference is constructive? So they're out of phase. The speakers are out of phase. That means this thing here is pi. So to begin with, they're out of step or out of phase. So that's a pi. They want the smallest distance for which the interference is constructive. So if they're out of phase, you put them right next to each other. If delta x is 0, that's destructive interference. We start putting them away from each other, and delta x grows, and so we want it to be constructive, so we get this. We want then delta phi to equal to just 2 pi. So I have this. Let me write this. Delta phi is equal to 2 pi divided by lambda delta x plus delta phi 0, which is pi. You might say, yeah, that's okay. Yeah, so the smallest delta phi here, the smallest non-zero will be 2 pi equals to, I mean, you could also use 0, but you would have negative pi, which means speaker 2 is in front of speaker 1, or speaker 1 is in front of speaker 2. It will just be exactly the same, but with a different sign, same magnitude. So you'll have 2 pi over lambda delta x plus pi. You move the pi here and you cancel. So you would have, when you move the pi here, you just have a 2 pi minus pi, which is 1. So you have a 1 on the left side. Here you have 2 over lambda, and then delta x. And so delta x, again, is equal to lambda over 2, which is 0.25 meters. 0.25 meters. Okay. So that's that. The next question here, let's do it, is, again, we like loudspeakers. It's in physics 2 you will do more of light, or physics 3. But for now, loudspeakers, sound. So two loudspeakers emit waves with the same frequency. So it's the same frequency along the x-axis. The amplitude of each is A. The sound is minimum when speaker 2 is 10 centimeters behind speaker 1. Let's see. So let's draw the x-axis. Right, here's the x-axis. I'm going to put speaker 1 at the origin. All right, so here's the x-axis. Speaker 1 is going to be at the origin. This is x equal to 0. x1 is equal to 0. x2 is behind it. Initially, x2 is 10 centimeters. Is it 10 centimeters? Yes, when it is 10 centimeters behind, x2 is 10 centimeters, or 0.1 meters behind. So there is a minus sign, really, technically, but this distance is 10 centimeters. It will be destructive interference. So this is destructive. When we have this configuration, we have destructive. Then you start moving speaker 2 slowly until it becomes constructive interference. So let's redraw the same thing. Here's the x-axis. x1 is still here. x2 is now moved here in front of it. x2 is 0.3 meters, so 30 centimeters. Now it's constructive. So at the beginning, when they have this configuration, it's destructive. When they have this configuration, it's constructive interference. And they give us a few questions. What is the wavelength? What's the phase? And what is the amplitude? And first, the wavelength, it's the speed divided by the frequency, but we don't have the frequency. So let's write down what we have. We'll start here. This is destructive. So we have delta. Let's write our friend. The formula here, delta phi is equal to 2 pi over lambda times delta x plus delta phi 0. Delta phi 0. And since since it's destructive interference, then this is equal to pi. So pi here equals to 2 pi over lambda times delta x, and the delta x, the absolute value of delta x, because delta phi here would be plus pi or minus pi, it's the same thing. So delta x is the distance from here to here, and that is 0.1 meters. 0.1 meters plus phi 0, or delta phi 0. And so let's move this to the other side and solve. So we have, actually I don't have the wavelength, right? I don't have the wavelength. So let's just keep it like that for now. Let's write it for the second case. For the second case, it's constructive interference. So on the left-hand side, so this is for this here. And for this one here, I'm going to write the same thing, but instead of delta phi being pi, it would be equal to 2 pi because it's constructive here. So I have 2 pi, let me write it here. 2 pi is equal to 2 pi over lambda, 2 pi over lambda times delta x. Delta x will be in here. I'm sorry, here x2 minus x1, so it's behind it. So this will be negative 0. Sorry, negative 0.1. Yeah. And in here, x2 is in front of x1, so it is positive 0.3, and then delta phi 0. Yeah, so let's do that. That's easier. So we can do this equation minus this equation and solve. So this minus this, 2 pi minus pi is pi on the left-hand side. And then you have 2 pi over lambda times 0.3 minus negative 0.1 times 2 pi over lambda. So that becomes 0.3 minus 0.1, that's a 0.4. And I have the 2 pi over lambda, 2 pi over lambda. And then I have 0.4. And the phi 0 just cancels, delta phi 0. So now I get to calculate lambda. So the pi goes away. So lambda over 2 is 0.4, or what am I doing? Yeah, I get on the left side, left-hand side, I have 1, and then I have 2 times 0.4 is 0.8 over lambda, and that gives me a lambda equal to 0.8. Okay, yeah, fine. Lambda is 0.8. So I found lambda. And then I need to find phi 0. So for phi 0, now you know lambda, you can plug here or plug here. So let me go here, plug in lambda, and get phi 0. So let's just go here. I have 2 pi equals to 2 pi over lambda. 2 pi over lambda, but lambda is 0.8. I know it now. And then times 0.3 plus 0 plus delta phi 0 equals to that. So let's see what we get. We will have 2 pi, and then 2 pi times 2 pi minus 2 pi times 0.3 over 0.8. So let's see what we get with that. I have 0.3 over 0.8. That gives me 1.25 pi. So delta phi 0 will give me 1.25 pi. So that is delta phi 0. Am I? Yeah, it is recording. All right, so that will be our phi, and it's 1.25 pi. If you like, you can. So if you're here and you add a 1.25 pi to the cosine, so that's pi and a quarter, or pi less than a quarter, which is 3/4 of pi. That's also the same. So you can put delta phi as 3/4 of pi. Now they say, what is the amplitude of the speakers if they are placed side by side? If they're placed side by side, then delta phi, I will write it here. Delta phi will equal to, if they're side by side, then delta x is equal to 0. So this part here is 0, and you just get this. You get just that. You get delta phi will be just delta phi 0 if they are side by side, which is equal to 1.25 pi. So let me just show you. Then the amplitude, if you remember, the amplitude was 2a times the cosine of delta phi divided by 2. Okay? Delta phi divided by 2. It's one of the equations in our book, which we have derived last time. It's in, if you like, in the book, it's equation 17.26 or 17.27. So 17.26, 17.27. And let's in multiples of a, what is this cosine here? So let's see what we get. And so the amplitude. I'm sorry, I forgot my absolute values here. It should be absolute, just because it's the amplitude, the maximum displacement from equilibrium. So if you do this, if you plug in here 1.25 pi divided by 2, you take the cosine of that, or you can put 3/4 of pi, try both if you like, you will get a number in front of a. So the cosine of this divided by 2, and then the cosine of the angle divided by 2, and then multiply everything by 2. And that gives you 0.765, 0.77. 0.77 times A. That will be the amplitude. Okay? That's the amplitude. And so it's not quite the maximum constructive interference, but it is constructive. I'm sorry, it's not constructive. It has to be greater than A to be constructive. The amplitude can be as large as 2A and as low as 0. So if it's less than A, it will be partially destructive. So this is partially destructive here. And yeah, so that's that. So let's go to the next question. Let me put away my calculator here and read the question. So it says, you are standing 2.5 meters directly in front of one of the speakers shown. So you have a speaker 1, speaker 2, and you're standing in front of one of them directly. So this is like a 90-degree angle. Okay. The speakers emit sound of a frequency of 686 hertz, and they're in phase. In phase. What does in phase mean? Delta phi 0 is equal to 0. And since the frequency is 686, let me write here solution. I suspect we will need the wavelength. The wavelength will be the speed of sound divided by the frequency. The speed of sound at 20 degrees Celsius at room temperature would be about 343 meters per second, and this is 686. And they gave us the numbers this way, so they're nice. 343 is half of 686, so that's 0.5 meters. Okay, so 0.5 meters. And so that's those are the speakers, and they say you were standing here, and then you start. I'm sorry, you're standing here and you start to walk away. It says, for what distances from the speaker, from this speaker, would you hear a minimum sound intensity, meaning destructive interference? Okay, destructive interference. So, how are we going to do this? Well, it's not that bad. The distance from here to where you are is R1, and the distance from here to you would be R2. And I know that R1 is just how far you are. You don't have to do anything. You don't have to use Pythagorean theorem or anything. But for R2, you're going this way, so it is 3 squared plus R1 squared that is equal to R2. So we conclude, let me write it down here. R1 is wherever you are. So, and R2 will equal to R1 squared plus 3 meters squared square root, like so. That is R2. Okay? Because it's this squared plus this squared square root. And we got our wavelength. Okay? And so let me just leave that there. And I know that delta phi will equal to what? 2 pi divided by lambda times delta r instead of delta x, now delta r. Because x, if you're just along the x-axis here, we're in 2D. Plus delta phi 0, but delta phi 0 is equal to 0. Because they are in phase. So I conclude that delta phi will equal to 2 pi over lambda times delta r. If I want minimum sound intensity, it means delta phi is an integer plus a half multiple of pi. So I want destructive, minimum means destructive. So I want destructive interference. That means I want delta phi to equal to m plus 1/2 times 2 pi. 2 pi. So let's plug this on the left side. So I get, on the left hand side, I have m plus 1/2 times 2 pi will equal to 2 pi divided by lambda. So let me put lambda for now. And then delta r. Okay, delta r. And you know this 2 pi goes away. Multiply, by the way, m here is equal to 0, 1, 2, and so on. Okay? Multiply both sides by lambda. Lambda is 0.5, so multiply both sides by lambda, so you get 1/2 times m plus 1/2, because lambda is 1/2, right, will equal to delta r. But what is delta r? Delta r, let's do some side work here. Delta r is equal to r2 minus r1. Okay, r2 minus r1. And that's equal to r1 squared plus 9 square root minus r1. So 1. Okay. And yeah. And if I want to solve for r1, I have to do some algebra here. I have to square both sides in order to solve for r1. Okay. So let's carry on. So by the way, instead of having this annoying 1/2, let's do it in general because lambda will be. Let me put here the lambda here. I'll just multiply by lambda. That's better than 1/2. So if I square both sides, let's square the delta r. So delta r squared will give me what? Let's square this. Will be this squared plus this squared and then minus 2, the product of both of them times 2. So I'll have r1 squared plus 9, that's the first one squared, plus the second one squared, which is r1 squared, and then minus 2 r1 times r1 squared plus 9 square root, like so. Okay, and we have to square this, and then why did I? Let's see here. I think I'm making an algebra mistake. I'm actually doing it a little bit the harder way. So let me back up here. Let me just back up here. Let's just back up. Let's write it here. Let's write down what this is and then continue. So I have lambda times m plus 1/2, and delta r is equal to r2 minus r1, which is r1 squared plus 9 minus r1. And instead of r1, I'm just going to call it r. That's okay. Let's keep calling it r1. That's fine. I should have just called it r from the beginning. Let's just call it r. R1 is equal to r. All right. We'll just name it r. And let's move this to this side. So we have added to both sides and then square. So I have this r plus lambda and then m plus 1/2. And I'm going to square this side. And when I move this to the other side and square this side, I just have the r squared plus 9. Okay? Yeah, that's way better. That's much simpler. Let's square them. So you get r squared plus 2 lambda times r times m plus 1/2, and then plus this term squared, which is lambda squared, and then m plus 1/2 to the power 2 equals to r squared plus 9. And something good happens, the r squared here goes away. Yeah, that's way better than I was doing earlier, because I would have had to solve like a quadratic and end up with the same thing pretty much at the end. Yeah. Okay, awesome. So let's move this to the other side and leave everything with the r on this side. So I will have 2 lambda r m plus 1/2 will equal to 9 minus lambda squared times m plus 1/2 squared. Divide both sides by this and you solve for r. Therefore, r will equal to 9 minus lambda squared times m plus 1/2 squared divided by 2 lambda m plus 1/2, and that's it. Okay. So that gives you r. Those are the distances at which the interference is destructive. So you go and plug in. If m is equal to 0, you calculate r. If m is equal to 1, you calculate r. If m is equal to 2, you calculate r. And that is it. Yeah. All right. So for example, if you plug in the numbers at m equal to 0, r is 17.88 meters. If m equal to 2, if m equal to 1, you get 5.62. If m equal to 2, you get 2.98, and so on and so forth. Okay. The important part is really the physics setup right there, and the rest is algebra. Okay. So that's the end of this chapter, chapter 17 of interference.